All right, so in our last video, we looked at nucleophilic addition to ketones and aldehydes. We said that aldehydes are going to be a little bit more electrophilic, and that you can have nucleophiles attack in under acidic or basic conditions. Really, the only difference between these is when that protonation event occurs. As we saw in the basic condition, protonation happens last, where under acidic conditions, protonation happens first. And we said that there's a wide variety of nucleophiles that can be used. You can have oxygen nucleophiles, you can have sulfur nucleophiles, you can have nitrogen nucleophiles, hydrogen nucleophiles, and carbon nucleophiles. The nucleophiles that we tend to see most often in organic chemistry are the oxygen-based nucleophiles, so that's kind of where I wanted to start to begin, and then we'll cover the rest of the nucleophiles as we go on. So let's go ahead and start with oxygen nucleophiles, and what I want to cover right now is just hydrate formation. And it's pretty straightforward. If you have a ketone or an aldehyde, in this example I'll just draw a ketone, you can have it react with water, and under equilibrium conditions, you can get what is called a hydrate, where water can act as a nucleophile and attack into that carbonyl compound. Again, this works with either aldehydes or ketones. And anytime you see two alcohols bonded to that same carbon, this is usually just referred to as a hydrate. All right, and like I said, it's going to be these aldehydes that are the most susceptible to hydrate formation, meaning the equilibrium for aldehydes tends to favor the right-hand side more than with ketones. All right, so let's take a look at some examples of this. And let's do some simple ones first. So for example, if we have acetone, if you react acetone with water, you could imagine that you might get some hydrate that is formed, where the water will add into that carbonyl. In fact, you can measure this, but you don't get very much. You get about 0.1%. And again, this shows that ketones tend to be way less electrophilic than aldehydes. So let's compare an aldehyde. Well, if you have formaldehyde and water, you can again mix this together and you can look up or investigate the amount of hydrate that's formed at equilibrium. And for formaldehyde, which we would expect to be more electrophilic, you get about 99.9%. In fact, when you order formaldehyde, normally what you're getting in the bottle is the hydrate, not formaldehyde by itself. Sometimes you might get paraformaldehyde, that's something else though. All right, so as you can see, aldehydes are way more electrophilic than ketones, like we said before, but let's investigate this mechanism more. And the mechanism we'll look at first is going to be acidic. So let's even differentiate these. So we'll do acidic mechanism first, and then we'll do the basic mechanism second. So let's take a look at the reaction using a simple aldehyde like formaldehyde. And all we need is some sort of acid catalyst. So I'm just going to write H+, and I'm going to make a note that this is going to be our acid catalyst. All right, so the first step of this reaction is just going to be the CO bond, specifically the oxygen, grabbing the proton from our acid catalyst. At this point, we will have an intermediate that is really electrophilic. It's super electrophilic because it's not stable with that positive charge. So if you have water floating around, this water is going to quickly attack into that carbonyl and kick up electrons to that oxygen. So now we've got a portion of our hydrate made. The water that attacked in, though, still has a proton off of it, right? So when we think about the water is this highlighted area right here, right? It still has two hydrogens, so all we need to do in this next step is remove one of those protons, and so I'll even highlight it and I'll say let's remove one of them, and I'll just write -H+. So now we can go ahead and we can show this forming our final product. But like I said, the acid that's put in is regenerated at the end, which makes it completely catalytic, which is kind of neat. All right, so let's jump into the basic mechanism next. And as you can imagine, the basic mechanism is going to be a little bit different. All right, and with the basic mechanism, instead of acid-base chemistry happening in the first step with the carbonyl compound, your base, I'll just call this B minus, is going to react really quickly with your nucleophile, all right? So in this case, water as our nucleophile has a proton. So we can show our base plucking that proton off of our water. And by doing that, we're going to make hydroxide, all right? So deprotonated water is just hydroxide. And I'll just show my conjugate acid so we don't lose track of things over here. So we've got hydroxide and our conjugate acid. At this point, this hydroxide is a pretty good nucleophile, much more aggressive than water in its neutral state. And it can attack that CO double bond and kick electrons up to the oxygen. All right, so let's take a look at this intermediate that we're going to get. So at this point, the hydroxide's added in. However, the oxygen, specifically this oxygen right here, is going to be left with a negative charge on it, right? So the question is, well, what happens in the next step? Well, we still have this conjugate acid floating around, right? So what could occur is we could steal the proton back from any sort of proton source, and we can form our final neutral product. And when you do this, you also regenerate your base. Oops, I'm actually a little bit wrong here. If you notice, I put a positive charge right here and here. There shouldn't be any positive charges there. It should just be neutral. However, when you look at this, the base is also catalytic. We put base in and we got base out. So with these reactions, it really depends on whether or not you've got acid or base around. If, let's say, you just have water, water can act as either an acid or a base, so it really just depends on the pH. All right, so let's take a look at a weird example before we go on. And it's frustrating because in organic chemistry, there's a million exceptions. And I wanted to go back to this example with a ketone, specifically acetone. I said if you mix acetone and water, and let's say you've got an acid catalyst, just a drop of acid, you might get a little bit of your hydrate. However, when you measure this out, it's still going to be 0.1%, even with that acid catalyst. It's a really, really tiny amount. And like I said, that has to do with the fact that the ketone in acetone is not very electrophilic. So let's take a look at a different example. Let's imagine that instead of CH3 groups, we've got CF3 groups on either side of that CO double bond. And we react this with water. And you treat this with an acid catalyst. You can get a hydrate formation where that water adds in. And if you measure the extent of the equilibrium, you'll find that it goes 99.9% to the product side. So then the question is, well, why is this occurring? Why is this ketone more electrophilic? Well, it kind of makes sense. If you think about what makes a good electrophile, it's something that's deficient in electron density, right? In this case, the CF3 groups are really, really polar. Really electron withdrawing. So they're pulling electron density away from that central carbon, which means that this is more electrophilic due to induction. those fluorines are pulling the electron density through multiple sigma bonds away from that central carbonyl carbon. So it makes it more electrophilic than, let's say, acetone, the example shown above. All right, so let's pause there. And then when we come back, we'll look at oxygen nucleophiles in other contexts.